Hello everyone! In this video we will continue to examine topic 5.1 electric fields, and in particular we will begin to unpack the concept of potential difference. So, in the last video we discussed the similarities between electric force and field and gravitational force and field, in part so we could introduce the concept of electric potential energy. We derived a formula for the electric potential energy, at least as can be calculated in a uniform electric field, in this scenario right here. And that is useful, but it's worth noting that that is not formally part of the core or SL-IB curriculum. However, this concept of electric potential energy as working exactly the same kind of way that gravitational potential energy is really important, because it will allow us to define a quantity that will be incredibly important in analyzing electric circuits later on. And this idea of electric potential energy, simply put, is that you can store electric potential energy by doing work on a charge in an electric field, either taking a positive charge from near negatives and moving it to near positives, or vice versa, and this is not true for gravitation, but if you take a negative charge from over here, you can store gravitational potential energy by moving that negative charge in the other direction, okay? A way of thinking about that is that if Q and X, or more accurately, Q and delta X, if we're thinking about changes in energy, are negative, then they cancel out and you get a positive potential energy. Using this formula will not be particularly important, but this idea that you can store energy in the arrangement or the position of electric charges by moving them in the field, and in particular, the intuition here is you always want to move them against the way they would want to go naturally. So how do you store gravitational potential energy? You pick masses up off the ground. Same for electric potential energy. You drag the charges to where they don't want to go, so to speak. And this is the same concept. So how does that apply to this unit? To introduce the application of electric potential energy, and ultimately this concept called electric potential difference, I want to just consider a very, very simple electrical circuit. We'll get more complicated ones later, but a very simple electrical circuit, where circuit just means a closed path, in which a battery is connected to a light bulb or lamp. Strictly speaking, this word for battery should probably be cell, so C-E-L-L. But for now, we'll just assume battery means the normal, everyday thing you would consider if I say the word battery. This is a picture of the diagram. This is a picture of the setup as described above, with a sort of incandescent light bulb and a pretty pathetic version of a battery. Okay, and in this picture, we will almost always represent these sort of physical situations by capturing their most important features in what is called a circuit diagram. And we'll see way more of these later. But the idea is we're going to clean up this picture and capture only the most important elements. The first thing is that we're going to have a symbol for different circuit elements, that is, components of the circuit. Our symbol for the battery is this right here, where we have a long line and a short line close together. That long line is positive, and that short line is understood to be negative. So that's the positive end and a negative end of a battery, or more particular, well, we'll get into that in a second. The current that we've discussed is going to flow this way. All right, so with a positive end over here and a negative end over here and a closed path between them, all right, the charges will move along the lines directed by the electric field. So the electric field is going to travel sort of along the conductor in this direction, and as a result, the charges will move in that direction. Notice I'm talking about the conventional current here. Okay, so the conventional current flows along the circuit this way, and in the meantime, it goes through this symbol, which stands for the light bulb. And the light bulb heats up and lights up, gives off light and heat. All right? So, what is happening from an energy perspective here? Well, that's the essence to understanding this concept of potential difference. So in the circuit, electric, read chemical, sometimes we call that chemical, but it's really the same thing. Remember that chemicals are just related to the electrons and protons, in particular ions. So the electric potential energy that we just discussed as an idea is delivered to the charges at the battery. So the battery is where that electric potential energy is given to the charges or stored. And the charges then deliver that energy to the cations in the lamp filament. In other words, as these charges move along in their electric current, they run into the positive ions in the metal of the lamp filament. When they do that, they heat up that tiny little filament to a very high temperature. That tiny filament gives off light and heat, and so energy that was delivered to the charges in the battery is then given off as light and heat in the light bulb. And that's the key essence to, or key element to what is going on in the circuit from an energy perspective. Notice conservation of energy applies. Any energy delivered to the light bulb will have to have been generated and ultimately have been stored in that battery. Okay? And the kind of energy is electric potential energy. So the electric potential energy is provided to the charges in the battery and then transformed to heat and radiation in the lamp. Okay? But we can ask ourselves how much, and that's a really important key question. How much energy ends up delivered to the charges? And the answer is, it depends on the source, okay? So what is the nature of the battery? And it also depends on the amount of charge. So the source is going to deliver a certain amount of electric potential energy to each charge. And then how much charge sort of carries that energy will affect the total amount of energy delivered to the light bulb. And in particular, if you want more charge, you have to wait longer. So it's sort of a rate idea. The battery gives a certain amount of energy to every coulomb of charge as it leaves the battery. And then it will continue to do so as time goes on. So if you just leave this hooked up, obviously energy is continually being delivered to charges here. And then those charges deliver that energy as light and heat in the lamp. So the answer to our original question, how much energy is delivered, depends on the source, that's their battery here, and then the amount of charge, where the amount of charge will usually depend on the time that you leave the circuit running.